of the lobes. They don't have blue anymore in the lobes.
Okay. Everybody back? Now.
Jen, got my pen. Black one.
Bladed crystal. Okay. Now I've just done this with some of you because I'll do this before we move on to the wonderful symmetry elements. Looking down the C-axis, what have I got? I've got rectangle shapes, so my crystal system is orthorhombic. Cool. Now this is just for orthorhombic system. We've got our C-axis. If we go back to our old Latin, the front to back, the A-axis is the short axis, the B-axis is the long one, right? The front to back axis is called the brachyaxis because it's short like a branch on a tree perhaps. That's the brachyaxis. The B-axis is the long one, so it's called the macroaxis, okay? Now I only want to talk about that for the orthorhombic system, but you could apply that anyway because we always by tradition have the short A-axis front to back and the longer one, the B-axis, side to side. So brachyaxis, macroaxis. So if I'm looking at this particular orthorhombic crystal, I've got the front one and the back one that are the same. There's only two. What are they going to be? How many prism faces do I need? Definitions, ladies and gentlemen.
3 or more.
3 or more. So if I've only got 2, they have to be pinacoids. If I've only got 2 the same on the side here, they're going to be pinacoids. If I've got these, if you can't see it, but you can have a look at the end, there's a tiny little face on these corners, and there's 4 the same. What are they going to be?
Sorry, Jen, we can't see. You're leaning forward. Aha, thank you.
Sorry, I lean forward when I'm eager. Sorry.
Yep, we love you for it, but you've got it. We can't see it.
Sorry. Well, you know, and if you don't tell me, I don't know. Sorry. So I've got 4 little faces on this crystal, 4 that are the same. So those little faces, even though they're not dominant, are going to be prism faces because there's more than 3 like faces. Now, they are parallel to each other. If not, then they're parallel to the C-axis. They're just at an angle, but the 4 of them are equal. Therefore, they are prism faces. Now, what sits above a pinacoid is a dome. Easy peasy. Above a pinacoid sits a dome. What sits above a prism face? A bipyramid. So in this particular crystal, above this crystal face here, I've got a dome. So I've got a pinacoid and I've got a dome. And by tradition, it's going this way. So I've got a parallel to that direction. I've got a macro pinacoid, and therefore above it, I've got a macro dome. On the side here, facing the front to back, which is the brachy direction, I've got a brachy pinacoid, and above that, if I've got a face, it will be a brachy dome. So on a crystal like this, I can have prism faces, and I can have pinacoid faces, and I can have bipyramids, and I can have domes. So when I put up the pictures before of topaz, if it's going to, it will often have domes. It's this side one, the brachydome, that is the major one. Whereas this one, if it was a crystal, the major one we've got is the one, the macro one, the front one, which is damburite. So we can get in the orthorhombic system, you can get a combination of all these faces. And of course, if there's a face at the top and the face at the bottom, they're going to be basal pinacoids. So again, if you know your definitions, then you can apply, when you're counting your faces and what directions they are. Now, the modern syllabus says sometimes instead of talking about domes, we can call them horizontal prisms. If you just want to be content with that, you can. If you like, but you still need to tell us about the pinacoids being macro or brachy, the long one being the macro, the short one being the brachy, and you will do that with orthorhombic with your crystals in there, which is why you need the loop, because some of these little faces are very small. Sometimes you'll get the diamond shape, but if it doesn't get to the point and you've got a little flat surface, we've got two of them, they're pinacoids. Okay? Or you might get two at the front and back, they'll be pinacoids. But they won't all be four the same because they won't be going in the same direction. So they will be pinacoids, little ones, not prism faces, because there's two there and there's two there, just the same as these, two there and two there. Okay, now when I go back to tetragonal, cross section here, A equals B, so I've got a square cross section, and I've got right angles, so I know I'm in the tetragonal system. But sometimes zircon wants to be its own boss, so instead of having, and this is zircon sometimes does it, some of the hexagonal ones do it. If you've got little bits of bipyramids, as you can see here with this one, they're off the corners. Here am I telling you that the bipyramids sit above a prism face, but you can get it this way. You still have to look for your angles and everything, because in this particular instance, we've got prism faces of one order, and the bipyramids have come as if there's been a second order of prisms, and so we've got the other order of bipyramids. But in general, you don't get that. In general, you get, because someone's been throwing out my crystals and I'm really angry, sometimes, mostly you'll get them sitting above each other as in my slides, but occasionally you'll get this. So that's why you've got to look. But I've got squares. I've got squares here, and I've got four faces the same because A and B are the same. So it cannot be orthorhombic. So then we start talking about prisms and bipyramids, because that's all there is apart from basal pinacoids in the tetragonal system. So you put all those bits of information together to decide your crystal system, and then you can decide how you're going. So if I said, oh, well, that's not above a prism face, that must be a dome, then I'll say, bye-bye, because there are no domes in tetragonal. So once you've worked out your crystal system, then you can label your faces accordingly.
So you're calling this bipyramid based on the angles coming when the top and bottom are pinacoids?
No, there's four prism faces, and there's top and bottom, so they're bipyramids. And I'm saying that normally that they sit above a prism face, but sometimes with zircon or sometimes with aquamarine, you'll get them in the corners of the prism faces, not over the prism faces.
So what happens to the top?
Basal pinacoids.
Yeah, pinacoids.
Yeah, sorry.
But why did you say that we rule out the orthorhombic?
We would rule out the orthorhombic because I've got a square, not a rectangle.
No, the orthogonal, what else is
Orthorhombic.
Yeah, okay, orthorhombic.
Okay, folks, can we move on to the good part of the evening? Now, these are imaginary things, just like when I talk about the A-axis, the B-axis, and the C-axis. These are imaginary things as well to help us describe crystals. These are theoretical things. You're really not going to do it in the lab. Some people want to understand how we get all of these elements of symmetry for each crystal system. Other people couldn't care less. And as I say, after Gem 1, you don't have to know. Now, what there is in YouTube is hundreds of YouTube presentations on crystal symmetry, elements of symmetry, crystal elements of symmetry, and there's a lot of them with beautiful graphics to show you exactly how you get them all. If you don't want to know that, we just know that for each crystal system, this is how many elements of symmetry you can get, but there's one that's the minimum symmetry that you must have to be able to say it's cubic system or hexagonal system or whatever. Once you've found that, that's the main thing you have to know. So even though if I tell you there's over 20 elements of symmetry in the cubic system, but I only want to remember the minimum symmetry for the cubic system, I only have to remember one thing, okay? So it depends how desperately you want to understand where these elements come from. If you don't, then don't worry, just commit a couple of these to memory, and really I don't think the minimum symmetries are hard to remember.
One more question. In the hexagonal system, do we draw the lateral axes to the middle of the face or to the corner? Like,
Wait, what did you mean?
I think it's the middle of the faces yet again. I'd have to check.
because in the picture it goes to the
The
corner.
corners, well, it's probably the corners. And to me, it doesn't make any difference from a practical point of view. It doesn't matter. If they've come from the corners, then the second set order of prism faces will come from the center of them. That's how you end up with 12 instead of 6. So it doesn't really matter if it comes from the center or if it comes from the corners. When we're talking elements of
shouldn't matter.
Sorry?
So in the hexagonal, I don't think it should matter. But
Well-
what about the trigonal? Would it come from the corners, or because it's 2 sets of 3s, right?
Yeah, 2 sets of 3. I don't think it does, because you're still, the way we work out these symmetry bits, I don't think it really matters. It's only this one, I'll show you.
Yep.
Okay, so the axis of symmetry is talking about an axis, okay? So these 3 are important to know, otherwise you will get lost. So an axis of symmetry is an imaginary line passing through the center of the crystal, about which we can rotate it and see how many faces we're going to see. So if I've got a crystal here like this, my axis of symmetry might go down through the C-axis, okay? Now, if I rotate, this is tetragonal, if I rotate this, hang on, I'll get my beautiful crystal, I'll just get a red biro. Okay, so the definition, if I find an axis of symmetry, so at this point in time, I'm going to say, there's my axis of symmetry, and I'm going to rotate it round that to see how many times I see that same face. So if there's my first one here, I'm going to rotate this around. I see that face, same face again, the same face again, and then I'm back to there's 4 faces. So I've got, if I use that axis, 4 times I get the same picture. So I've got one axis of 4-fold symmetry using that direction. This is why I said you might not like to understand all this. All right, now, it might be easier to show you this one. Okay, so this is the tetragonal. So again, yeah, this is the one I've already written on. So if this is the direction I'm going to call in my axis of symmetry, I'll turn that through 360 degrees and see how many times I see that face. That's one axis of 4-fold symmetry, because I've come across the same face 4 times. Okay, now I might decide, all right, I'm going to turn it that way and put an axis down there. Now, what am I going to see when I turn that through 360? How many times will I see that face?
2 times.
Only twice, and I'll see another one that's twice. So each time I choose a particular direction and I rotate it through 360 degrees, how many times will I repeat that face? So with any crystal system, I can choose a lot of different directions and rotate that crystal to see how many times I will repeat that face. So there's just not one direction that I will get, but each different direction I choose, when I rotate it through 360 degrees, I'll be able to see how many faces. Now, you don't need to do this in the lab. This is just to show you how they work out symmetry, and it's why the symmetry for a trigonal system is different than the hexagonal system, because when we start rotating a crystal that's got two sets of three faces, you get a different symmetry response than if it was part of the hexagonal. That's why they've divided them up.
But in the last class, you said we look through the C-axis. So in some videos, they recommend looking through the C-axis, but now here we're looking from the sides.
I look down the C-axis when I'm trying to identify the crystal.
Not the symmetry.
Not the symmetry. Okay. So if I'm trying to work out how many times I can see a symmetrical thing, so because a cubic system is so even on all sides, that system has the highest number of different ways I can find symmetry with an axis when I turn it through different directions of the stone. The second highest is tetragonal, right through, because as the stone gets more or the crystal system gets more asymmetrical, there'll be less and less numbers of ways I can turn it and get a lot of symmetry happening. So that's the only definition of the axis of symmetry. In what direction, if I rotate it, how many times will I see that same face appear? So that's axis of symmetry. And as I say, online, they can show you with lots of diagrams that move how, all right, I'll start from here, I'll start from there, I'll start from there. So all these different elements of symmetry will add up. The next one they do is plane of symmetry. So this is now a plane, an imaginary plane. We're going to divide the crystal in half and put a plane right through that crystal. So going back to the tetragonal, I can put a plane right through, down through that C-axis there and end up with the same thing on either side. If I turn it that way, I can do the same thing and I've got two equal sides. This way, I can do that and I've got two equal sides. Even on the corners, if I cut it from one corner to another corner, can I get a mirror image of two? So two planes of symmetry. Basically, do I get mirror image from a particular direction? So with a tetragonal system, I'll get many more examples of how many ways I can get mirror images. I know you're all excited about this. I can see it on your faces. Okay. Now, the other part of symmetry is a center of symmetry. So if we have a point, if we put a line through a crystal, through the center of a crystal, can I put it from a direction through there and come out on the other side equidistant? So does this crystal have a center of symmetry? Can I pass a line through a particular point, go through the center and come out the other side and at an equal distance? So can I do that with this? Yeah, I can, can't I? Whereas there is one crystal system right at the very end where you can't even do that. So as you get through them, there's less different types of symmetry that you can get with each crystal. And as I said, this is only for theory. And again, if you're doing a whole crystal, it might ask you for the minimum symmetry for a crystal system. It's usually only the minimum symmetry you have to remember, not the whole lot. So if I tell you there's 20 odd elements of symmetry for the cubic system, I don't want you to go home and commit them all to memory. I'd rather you leave space in the brain for other things.
So how do you answer minimum symmetry?
Okay, so there it is. So that is something you can commit to memory, because the minimum symmetry means there are 4 directions where we can rotate that to get a 3-fold symmetry. So it is written 403. So you have to remember the cubic, and that's easy because you know that's got the most, as this is the minimum requirement. So if you've got a crystal like sometimes pyrites that doesn't grow the maximum number of faces, it still means the minimum symmetry for that crystal is there. It has to have 4A3 to be classed as the cubic system, even if it hasn't developed all its faces.
This bit here?
Yep.
Is that what I should know?
Yeah.
And I don't have to worry about the rest?
Well, I don't think so, no.
So that's
But
the
I didn't
most
say that.
important thing.
But I didn't say that.
Okay.
You got to know it all.
Right, all right.
Okay, so in this one now, how easy is it to remember the next one? Tetragonal system has got 4 sides when you look down the C-axis. What's its minimum symmetry?
1A4.
1A4.
Huh?
What's hexagonal?
1A6.
1A6. So without even having to remember anything, you can now remember the minimum symmetry for, well, quartz cubic 4A3. You just remember that. The next one's 1A4. The next one's 1A6.
Sorry,
Trigonal.
What
Well,
does that
so-
even stand for?
Yeah, so there's four, so the cubic one is like four sides,
4 directions.
four
Where you
directions.
turn it around through 360 degrees and you see the same thing all the way around.
Yeah, but what's the 3 stand for then?
So I might have not, so here's the
Four axes
first
of
one.
threefold symmetry.
There's 3 more directions and I get back to the same one. So through 360 degrees, I see one axis of fourfold symmetry. And there is, so with tetragonal, the minimum is that if not all the faces are developed, there will be at least one direction where I can turn it around and have one axis that's got fourfold around it.
Sorry, I don't understand why it's not 4. Sorry, so the first one is that there's 4 faces, but what's the threefold?
Oh,
That's because you take it through the corners, not through the face.
Ah, okay.
so there's
4
different
axes through the
directions.
corners, 4 axes, and if you rotate along that axis, you get 3.
See, Phoebe's he's
Okay.
been online to
I
see
don't
some of this.
understand it.
Something.
So the thing is, if you want to work out where these numbers come from, you go online and you watch one of these men do, or women, do, and they've got all of these lovely graphics, so you can see them turning and moving.
Yeah.
So, but if you don't want to do that, now we've just said hexagonal is one direction where you see you the same thing 6 times, okay? Trigonal, because there's 2 sets of 3, the minimum symmetry in there is 1A3. So none of those are hard to remember, really, are they? So this is why I don't spend a lot of time here. I would rather be explaining this, because you'll get more marks for getting this right in your prac exam than half a mark remembering minimum symmetries. And as I'm saying, I'm happy to go through and showing them all, but I would rather spend the time on showing you other things that will get you more marks, especially when you don't have to see that or know about it next year. It's purely for the theory of it. And if I told you, as I said, all of the elements of symmetry, all the different directions you can get is a lot more than that, but the minimum symmetry or the essential symmetry, they might call it essential symmetry. This is the minimum that you can have to find on a crystal for it to be in a particular system. So Google in YouTube elements of symmetry, crystal elements of symmetry, and you can watch them till the cows come home. You can have a different one every night for a fortnight if you want. But if you don't want to understand it all, I suggest that that's what you learn. Okay. No, but for your theory, if you know those 3 definitions, one's an axis, one's a plane, one's a center, how hard is that? So they're not even difficult to remember. It's just the concept of getting your head. If you wanted to see all of the elements of the symmetry for the cubic system, there's a hell of a lot of them. And I don't even have a cubic crystal to be able to show you. So I'm abrogating that responsibility. But if you know some of these tables, that's where you've got to go. So all up, there's 13 different axes of symmetry for a cubic system and 9 planes plus a center. But I've put it in red. That's what I want you to learn. By the time you get down to orthorhombic, that's all there is. But the ones above that have more elements of symmetry. So who wants to just learn the minimum symmetries?
Do we need to know the planes as well? Do we need to know
So
the
just the
planes?
red bits, yeah?
Yes, the red bits plus the bottom 2, that first column. So 3A2.
So 6 of those.
Yeah.
is, right? Because it's really hard.
So the orthorhombic,
It really
and monoclinic have only got that. That's the minimum symmetry is what they've got anyway. There's no, that's it. So there's not a lot that you have to learn there really. It's only if you want to understand it all, and I applaud if you do.
Jen, sorry to interrupt quickly. So for that half a mark thingy, like you said, just the minimum, what kind of questions would you can you throw one off the hat, like?
All right, they might have a crystal diagram for a
Okay.
question, and they will ask you just like your practical crystal system, forms, habit, name the crystal, minimum symmetry.
So that last bit, the minimum symmetry is one of those red bits.
Or if it's orthorhombic, the minimum symmetry is that, because that's all there is.
Okay.
So you need to know the 3A2 and the 1A2 as well. But from the previous one, that's it, okay?
So,
Jen,
yeah, sorry, when you said write in shorthand notation, something like that, with the, the workbook, so which one of these bits is shorthand notation?
Well, they all are, except you have to listen to what they're asking. If they ask you for the axes,
Yes,
they're talking A, B, and C.
okay,
If they're talking symmetry,
yes,
they're talking that last column.
okay,
So you have to read the question carefully. Are they talking about A equals B equals C and all angles are 90 degrees? Or are they talking minimum symmetry? You have to read the question correctly to give them the right information.
okay.
Jen,
And if they want to ask, for instance, how many planes of symmetry in the cubic system and you haven't got a clue, you'll lose half a mark.
Okay.
the reason I'm asking is I did one of the practice questions and it was asking for all the planes and axes.
Yeah, I know. Well, you won't get that. That's good for your practice questions to see if you understand. But for an exam, I don't think I've seen a paper where they've been only asking anything much more than minimum symmetry. So.
Okay, I just wanted to put that into perspective because when I came across it, I was just like, ooh.
Oh, well, but even if you want to learn more, look at the tetragonal. We know it's 1A4 for minimum symmetry, but it's 5 and 5, then 7 and 7. If you want to commit some of that to memory in a table, by all means do it.
No.
Well, this is why I'm saying I'd rather spend time on other things that you need for your theory and practical than this. It is interesting, but if you don't want to know it, don't. There's one or two things like that in optics I might say the same thing to. If you don't want to understand, just learn the formula, that's fine.
Yeah.
It's up to you.
What's,
So if you know the definitions of those three elements of symmetry and you know minimum symmetry, yep, what was that at home?
what's that sentence down the bottom about C? C can be variable in the with quartz and tourmaline.
The centre of symmetry, yeah, because we've given an overall thing there for trigonal, but some of them it's not so easy to necessarily have a centre of symmetry or not. But so in general, they probably won't ask that anyway. So I've just put that there to be pedantic. That's crystallography 202. We're sticking with crystallography 101. Like there's other ways if you get papers from, say, the GIA, Gems and Gemology, they will talk about the Miller indices. Once upon a time we had to learn those. These make your eyes spin. You don't need to know that anymore. I put a slide in just to show you because it's another way of annotating three-dimensionally so everyone around the world's on the same page when they're talking about a particular face in a crystal. But you don't need to know those. But once upon a time we did. Okay, twinning's easy. Twinning, again, a definition, two or more portions of that same mineral, be it quartz or whatever, have grown in such a way is that they have a plane in common. So it's not just two crystals growing next to each other or a cluster. Somehow something's happened and they've got a common plane because it's been one crystal that's ended up growing into two, or in chrysoberyl's instance with cyclic twinning, more than one direction. But something's happened with heat and pressure during formation or after formation to cause a difference in direction and having a common plane. So definition of twinning, they usually have a mirror image where they've moved, and some of the different types of twinning you can get is perhaps linked to whatever crystal system you're in. That happens sometimes to particular crystals in particular crystal systems, so that in the cubic system, often we will get what we call mackles with diamonds and spinel. It's a contact twinning where they turn. You tend to get that more than you do in other crystal systems. So sometimes it's a matter of, and this is another theoretical thing, except for it is important to know about these reentrant angles. So they will ask you for a couple of marks about the different ways a crystal can twin. And we can have contact twins where, as I just mentioned, sometimes the crystal halfway through will turn. So they've got a plane there that's in common, but the crystals change directions. And so we have a rotational like spinel or diamond. Geniculate twin is where they've changed direction. Geniculate's like knee. So you get this thing that goes like this. And if it's a different crystal rutile, the angle with that twinning will be different than, say, a different crystal that might also, zircon and rutile will give you geniculate twinning in the tetragonal system. The angle between that plane, that join plane, will be different depending on the crystal, but geniculate's this idea of like a knee bend. That's what geniculate means. Repeated means that for some reason, ruby does this. During its formation or afterwards, there's changes in heat and pressure. So the ruby's growing this way and all of a sudden, let's grow that way. Oh, let's grow that way again. So we get these planes where the direction of the growth is slightly different, even though it's still the same crystal, they get changes in that direction of growth. An interpenetrant, I'm sure you've all seen, gorgeous little pyrite crystals where they're growing in on top of each other. That's the other sort of twinning. So mainly, this one is not a mackle, that's an interpenetrant, but that one there is a mackle. So it really doesn't look, instead of an octahedron, it's this flapping sort of thing. Diamond cutters hate mackles because they can't cut them, because it's this zone that's like a knot in wood. It doesn't work for you. But now that we do laser cutting of diamonds, no problem. So when you see this spinel and it's changed direction, so you've got this flat triangular thing here, but what you can see is the plane where it's gone across, there's a V, there's a V there. We call that the reentrant angle, and that's an indication that twinning has happened in that particular scent. So with a quartz crystal, they can twin, in other words, change direction and have a common plane there. There's more than one direction, more than one type of twinning. Some are on a level where it's only inside the system and you can't actually see evidence of it on the outside particularly. But particular twins will have a particular angle. You know, they look like rabbit's ears. So this, and here again, we have got a reentrant angle there. So we've got a reentrant angle and a reentrant. Do we care about that? Well, in Gem2, when we look at chrysoberyl, and we know a lot of chrysoberyl has been started life as that cyclic twin looking pseudo-hexagonal. Even if it's a cut stone with the microscope, sometimes we can see evidence of these little V's, and we can say straight away that's twinning to give us help to say that's chrysoberyl. So, yeah.
Sorry, Jen. Just the previous slide, because we both snow snail, we missed it. Not previously? Yeah, that one, okay. We'll be very quick.
It'll be in Moodle, so you
Oh,
can
yeah, all right.
you can download it from Moodle. So the next bits after that are just showing you examples, but basically know the definition of twinning and have a couple of examples there. And you know, so lamellar or polysynthetic. Polysynthetic twinning is this layering that we get in a ruby. Lamella often is from something like labradorite. I've got a sample of labradorite there, and we can see stripes in it, and it's these changes of direction. Sometimes with moonstone, it's two slightly different feldspars, but we get the effects of it, sometimes with colour. So again, these little V's, and sometimes in the cut stone, they go through the crystal and we can actually see them under the table with a microscope. And if you can see those V's, there's not too many cut crystals, cut faceted stones that we might see that happening. But it does it with chrysoberyl. This is really, really rare, but again, spinel, so these funny things can happen. And so we've got this cyclic twinning again, so it looks pseudo-hexagonal, even though spinel's from the cubic system, but you're never going to see one of those anyway. Has anyone heard of Jedi spinel? Who said, yeah, aren't they lovely?
Incredible.
They're these really very, very small area, and I don't think they'll be there for very long, of these very bright red spinels, and they're so bright they call them the Jedi spinel because they've had no influence from the dark side. In other words, there's no iron or anything in them, so they're this beautiful fluorescent, and they call them Jedi spinels. You can look them up on the internet. So,
Where are they from?
Myanmar, aren't they? Yeah, small area, small mine in Myanmar. And some of them are better than others, of course, because they're not all uniform, but you can look up Jedi spinel. Aniside, that is. Okay, so rutile can be brown or orange, and that's what that looks like. And it was called geniculate because it's like a knee bend. And you can either do that as the crystal itself or inside gemstones. If it's an inclusion, you can sometimes see twinned rutile in something like a ruby, because sometimes you get all of the twinning on these little tiny baby inclusions of rutile inside the stone. Oh, sorry. So this is inside a stone. That'll be inside a ruby, and they're all rutile inclusions. But if we look carefully, you'd see that there's a lot of geniculate stuff happening there. Again, that's a whole mix of crystals together. But you can see the knee bend stuff, can't you?
So wait, sorry to interrupt. When you say reentrant angles, which bit are you the pointy bit?
The V. This
The V.
V. See that V?
Yeah.
Or here's another set of crystals here because there's a few of them. There's a V. Oh, there's another V there. There's another V there because there's a whole cluster of crystals, but each of those crystals are twinned, and you've got that V, that re-entrant angle, because that's pointing to the plane, common plane between the two parts of the crystal that decided to twin.
Okay. Thank you.
Interpenetrant, they look as if they're penetrating each other. Pyrites does that often. It's quite cute. Sometimes the interpenetrant ones are little, but they're quite. And I've seen people, if you're lucky, you can drill a little hole, and you can make a little pendant. Although it's a bit pointy, but you can make them into a little pendant. They look quite cool.
Yeah, cute.
Now, pyrites usually comes as a cube, but again, you get all sorts of things. Now, this one's odd here because it hasn't developed the right sort of faces. But if they found the minimum symmetry, which was 4A3, even though it hasn't developed all its faces, it's still part of the crystal system. It hasn't got its maximum symmetry if it hasn't developed all its faces, but it's got the minimum symmetry, so they're happy. Yes, it's still pyrites and it's still in the cubic system. Interpenetrant twins. And lamella is this repeated, and that's a type of contact twins. Now with this, you don't really see reentrant angles because they're just lamella. They haven't changed a lot of directions like geniculate or interpenetrant, so they're just on top of each other. So we see these, where's my mouth, stripes here. And those stripes, that's to do with lamella twinning, and it's to do with why we get those beautiful iridescent effects in labradorite. So you need to know about crystal structure to explain colour in gemstones later on. Polysynthetic twinning means that we've got these layers in the where it's changed direction in the ruby. Now, you can't really see the layers here, but on the edges of the twin planes, you get evidence of these needles. So we can see evidence of the twinning, or this one under a microscope where it looks like Venetian blinds, because we can use special things on the microscope and actually sometimes see the evidence of the twinning in that stone. And that's a nice thing to find if you know about twinning, because we don't get that in a synthetic stone. Except really, really rare. There's always a but. Okay, those you don't need to know about anymore, but I think it's in your notes, Justin. And in your notes, if it's written in blue, it means you don't have to remember it. I wish the elements of symmetry were written in blue, but they're not. So you do need to know about the elements of symmetry. Millirometries, they're talking about the point with the A, B, and C, and they talk about how you just define each of the directions. And in this, you can see how sometimes this is, even though they're talking about Miller indices, you can see sometimes how they can divide a crystal to see planes of symmetry. See those? You can see planes of symmetry with those, can't you? From different directions, okay?
Wow.
And that's what you will see online when you go to YouTube. They will show you with moving directions all the different ways where you could possibly, now these not so much, they're just showing you how to describe particular directions, but those are actually showing you some planes of symmetry that you might be able to find. Which crystal system has the most elements of symmetry? Cubic. What is the minimum symmetry for the tetragonal system?
184.
Hexag. Who said that?
What was the question again? Sorry.
Minimum symmetry for tetragonal system?
184.
104. Tetra 4. Minimum for the hexagonal system?
186.
And so if trigonal's half that,
183.
it's really difficult, isn't it? Okay. So, there are lots of definitions, but truly, if you can learn them as you go along, even while you're doing other things, the chemistry and I think crystallography has probably got the most definitions that you need to know. But they're short and they're logical. And three of those are your symmetries, you know, the axis of symmetry, center of symmetry, you know, all of those things, they're quite easy, same as the definition of a mineral, etc., etc., etc. So, and do yourself little charts, little tables as things. Okay, now, if there's a couple of red flags there, first in best dressed, because there's one short bit, and I'll do a drive-by for lesson 3, because lesson 3 is really easy, no difficult concepts, it's only things to learn. So I will swap this over and hopefully not lose anybody and go to the other, this one. So I'll let you walk around for a couple of minutes if you'd like to. I'm going at the wrong.
No, we're going to the number 3, right?
This is lesson 3.
Yeah, I got it.
So lesson 3 I chose to do after lesson 5 because a lot of it means if you know a little bit more crystallography, it makes sense. So you all need to get up, turn around 3 times. You see, I see in Instagram there's a lot of Chinese classes and they're amazing with all the little kids.
Yeah.
They stand up and they do all these really fast and furious exercises and then sit down again.
Yeah.
Sometimes
That's
it looks
very
so good. We should all
We
be
should all
doing
do
that.
that.
They
That's
do
our
crazy ones though. It's like
I
they
know.
go
And
nuts.
there's
Yeah.
one I saw where they're out in the playground and they're in a circle, a whole big circle of little ones, and they're bouncing balls and they have to jump to the next 2 bouncing balls, and they're just so good for coordination and everything.
Yeah.
Right, the 4 types of twinning. So we've got rotational, repeated, interpenetrant,
Contact,
contact,
which gives you,
rotational and repeated,
yeah,
and then
and interpenetrant.
is he on his own or is he part of contact?
No, he's on its own.
He's on
But
its-
then if you look up different sites, that's the way our notes describe it. There are other systems online that will describe them under different headings. So,
And the 4th one is secondary twinning?
yeah, probably,
Ish.
because that's still a contact twinning.
Right.
But if you talk about rotational and interpenetrant and lamella, which is lamella and polysynthetic, you know, you can divide them up whichever way really. But
Right,
if you,
because that's a question is that the workbook that says, name 4 types of twinning. So if I
So-
were,
contact rotational, genicular,
sorry, again,
contact rotational,
yes,
come on,
contact repeated,
Repeated.
repeated, which
repeated,
is lamella or polysynthetic. If you want to, you can divide up lamella and polysynthetic, and
Yeah.
interpenetrant.
yes, and then secondary twinning.
Well, the secondary twinning is really the polysynthetic twinning, whichever way you want to call it.
Jen, did you, the AC is so cold in here. Did
Turn
anyone
it
turn
off?
down a little bit?
Oh, absolutely.
Crazy.
Is it crazy?
Yeah. Thank you very much.
I want you to go to sleep.
Is this upside down as well, or only the?
Okay, are we still with me at home, guys?
Like that.
Doesn't go upside down?
Yep, still good.
Cool, okay,
Yeah, we're here. Yeah, all good.
all good, cool.
Well,
Now
is
for
it
the,
also like this?
Oh, like
for the flexi
Yeah, no,
students,
like this.
because I won't be, when we do our tutorial, which is April, our first tutorial, I can show you some of these things because I won't be showing you, you'll be looking at me, not a PowerPoint. If you want me to show you some of these things in our tutorial and we've got time after the workbooks, we can do that.
I think that'd be really helpful.
Good, okay.
Great, thanks, Jen.
Now 3 people bought crystal sets. I want you to check and see if any of them mention tourmaline and rhombohedra, because you now know I want you to call them, with tourmaline, I want you to call them trigonal pyramids. So they might be called rhombohedra because that was the old way. So just double check of what's written on your bags for tourmaline and get back to me.
Okay.
Okay, terrific, thank you. Okay, any questions so far before we swap to question 3? And I'm going to have another one. You might get some red frogs for
Yes, but this
optics
is also upside down.
occasionally. Okay. Oh, one's gone.
So when you said Ruby, it suddenly decides to do that and that, that's a repeated system. So wouldn't that also be geniculate, like a knee shape there? No.
And can be geniculate be upside down as well? Inverted
Geniculate-
V?
Oh, yeah, any
And-
direction.
yeah.
And lamella twinning, like in, you can have a basal level parallel to the
vertical.
basal, or it can be parallel to a rhombohedral face.
Okay.
So sometimes when you see a crystal, they'll be at an angle because the twinning has happened in that direction, not that direction. If I'm looking at the C-axis, sometimes that happens, sometimes that happens, depending on, because it's gone parallel to the rhombohedral face rather than the basal plane.
And is it like a cleavage, like where there's where it can break in along that?
Question, lesson 3 coming up. They call, or some people call, parting a false cleavage. There is a difference.
Yeah.
Has George, no, he hasn't left, he'll be coming back.
Yeah, he's just getting a cup of tea.
Random question. 42. Do you know where that comes from? 42?
No, it's random.
No, Hitchhiker's Guide to the Galaxy.
No.
And they spent millennia, millions and millions of years with this computer to find the answer to life, the universe and everything. And they're all waiting expectantly, and the computer just says 42.
It's like AI. That's AI.
What's the explanation for that though?
I don't think
Anything?
there is.
No, there was no logic or explanation.
It was.
I think
it's
a repeated number in nature.
42?
Oh, really? Was that in Hitchhiker's audience, or was it a scientist?
Or maybe it was something else. Yeah, it's like then like if you look at certain planets and like Fibonacci sequence and there's all these things. Maybe I read it afterwards or something along those lines. But it's like a repeated number in like history, nature, like it's like weird. It's like weird. If you want to go down a rabbit hole, everyone.
Check out the 42. Okay. There you go. I don't know that Richard Adams knew a lot about mathematics, but I don't know. Somebody might have told him to use 42, or he's just.
Douglas Adams.
Sorry?
Douglas. Douglas.
Douglas Adams, not Philip. Philip Adams we listen to on the radio, sorry. Sorry, thank you. Okay.
Love Philip Adams.
I look at the wherever I can find a couple of bit of data. Anything to keep me going.
Okay, well, as I say, this is going to be a drive-through because there's not a lot of explanation that you need from me. And same with any PowerPoints that any lecturer does. If it's not mentioned in the PowerPoint, it does not mean you won't be examined on it. It's just like me spending more time showing you an orthorhombic crystal than spending 5 hours showing you how to find all the elements of symmetry in a crystal.
Yeah.
It is our choice what we spend more time on. And so some things that don't get mentioned very much, it's because they probably don't need a lot of explanation like some other things do. So lesson 3 to me is one of those. They're simple concepts. So we're back to beauty, durable and rare. And lesson 3 is all about the durability side of a gemstone. We know what's beautiful. We sort of know what's rare. I don't think everything in this world, and if anyone has done a course with me in the daytime, it's done quest pictures like that because an operculum is the door for a sea snail. And in Victorian times, they thought it was the prettiest thing on earth and made a lot of jewellery out of it. It's very soft. It doesn't take a good polish. It scratches very easily. There's no chatoyancy or anything there, but it was classed as beautiful, but not in my book. So beauty's in the eye of the beholder.
And is it still considered beautiful in jewellery?
Well, you can still get it.
I reckon it's beautiful.
Well,
It's
nothing's
mostly
pretty.
considered rare, wasn't it? Like the value was in the rarity of it.
Maybe it was
think that
some
probably
rare
did,
because you
yeah.
probably had to send someone off to find sea
And
snails.
you have to like go to the bottom of the ocean and scrape them off and hold your breath.
But, well, or they could have done it like the original natural pearls before we started culturing them, say off the coast of Sri Lanka or up there. They just sent the divers down to hold their breath for, 10 minutes or something, and they'd bring them all up and they'd put them on the beach and they'd leave them in the sun to rot. And then they could go back and just pick up all the pearls that had sort of, they didn't have to sit there and pry open the oysters or anything. Maybe they did that with the operculums, I don't know. But anyway, maybe they thought they were more rare than beautiful. But even so, there you go. Okay, so all of these physical properties are about, they are going to influence the durability of your gem. And of course, you need to know about the durability, because if someone says, I want as an opal as an engagement ring, most of us would probably like to suggest that they don't. Because the hardness of opal is way down, like 3 or 4. So we don't actually want stones that are not durable if you're going to wear them all day, every day. So all of those different things. Now, as I've written as a summary above the top of that, it is concerned with what it's made with, like carbon, aluminium, or whatever elements are in that structure. And then it depends on how strong those bonds are, like carbon with a diamond or a graphite. It depends what the neighbours are, how closely bonded they are to the neighbours, and of course all of that goes into the crystal system as well. So the harder a gemstone, for instance, the better polish we can get on it. So that looks more bright and sparkly than something that's soft like an operculum that doesn't give you very much shine at all. So any of those things there are important, and they are all to do with now. Probably one of the few ones out of that are not associated with crystal structure could be which one? Well, 2 maybe, thermal conductivity or fracture, because anything can fracture, anything can break. So whether it's a piece of glass or whether it's a diamond, things can break. So obviously, what do we call a piece of glass or man-made glass? Paste. Amorphous or non-crystalline. So the non-crystalline things can still fracture in different directions, but most of the other properties are connected to the crystal structure. So most of those are related to being crystalline substances. So again, cohesion is just the name that we talk about, the electrostatic forces holding those elements together in whatever pattern they've chosen to solidify in. And that's to do with the bonds and the atomic structure. So how hard it is to pull them apart is the opposite of, how tightly they are. How much. Oh, okay. All right. Let me see what I did. I thought I just had to change. Let me go back again then. Let me see. Oh, Leo said I only had to just change PowerPoint, didn't he? He did say that, didn't he, guys? All right, let's get rid of that one then. Now, what can you see now, guys?
Don't say. Oh dear.
Maybe you have to go stop presenting.
Stop sharing, and then we'll start again. We'll try again. Here we go.
Just above it, it says lesson 3. So, lesson 3.
That's why I told you all to listen tonight. Between the lot of us, surely we can work it out. Is that good? All right. Sorry, guys. I'm glad you pipe up. This is where we started. And I was just talking about durability and the operculum. And now these properties here. So cohesion just being these forces of attraction holding all of the elements together to do with who they are, what their bonds are like, what their neighbours are. So cleavage is the first one. Now you have to be a crystal, you have to be crystalline to have cleavage, because this is an important definition, because cleavage is the property of a mineral, a crystalline mineral, to split in certain defined directions that are parallel to a crystal face or possible crystal face. So just in case of, like a rose quartz or something, you might not be able to see the crystal face, but the internal structure being crystalline means there is a face that should be there even if we can't see it. So cleavage will break in particular directions according to that crystallographic nature. Now that means it will break in a direction that has a weakness. It is a weaker bond. So if we want, thank heavens, with a diamond, we may want to cut a diamond. We have to find that direction of weakness to actually be able to cut a diamond into two pieces, by putting a wedge in and hitting it with the hammer and hoping it splits and not shatters into two pieces. So because we have properties that can vary in direction, because we have an atomic structure, some directions the bonds may be slightly weaker than other directions. So in that direction, parallel to a crystal face or possible crystal face, we can make a break that will yield more or less clean faces. So it will look like maybe a crystal face because it's in that same direction, but there are clues to tell us that it is a cleavage plane. So that's why when we've got a topaz crystal, cleavage on a topaz is parallel to that basal plane. So when with a topaz, it could keep breaking over and over again. So if we tried to cut a gemstone and polish that surface, we would never get anywhere because it would keep breaking. We could never polish it. So if you cut a topaz as a round, brilliant stone, all of those 57 faces cannot be, none of those faces, those facets, can be in that direction of the basal plane because you'd never be able to polish it. It would just keep breaking off. So,
sorry, why?
Because in that direction of the basal plane for topaz, that is a cleavage plane. So it will keep breaking in that direction. So not once you try and polish it and it will just keep on breaking in that direction. So it will break parallel to a crystal face, leaving more or less smooth faces. Okay. Some crystals have cleavage planes, some don't. Quartz doesn't have a cleavage plane. So, and then we can talk about that cleavage. Is it is it going to happen in more than one direction? Is it a less than perfect cleavage plane when it makes? So sometimes there is more than one cleavage plane, more than one direction of cleavage, 4 directions for fluorite, for example. So something like kyanite, the bladed crystal, has 2 directions. Some of them, it makes it very difficult to cut if they've got to make sure that they don't have any facet ending up on a cleavage direction, a cleavage plane. So you need to know a definition of cleavage. You need to know some examples, which will cleave easily, which will cleave to give really smooth faces. So mica is one of the examples. If you've ever seen any mica, all you have to do is sneeze and it'll break into these finer and finer layers all the time. They're like pages of a book. It will just, in that direction, keep on doing it all the time. I'm labouring that point for a reason, but it just keeps in that direction, keeping going, which is why I said fluoride starts life as a cube, and if I drop it, there are 4 directions of cleavage planes in fluoride, apart from it being soft. Don't throw it in with your chains. There are 4 directions of cleavage yielding. It cleaves easily, perfect planes, and it will end up as an octahedron. If we drop it, it will end up as a smaller one and a smaller one and a smaller one because they're the directions it breaks, and so you just get smaller and smaller fluorite octahedra. So you need to be able to look with your loupe and decide is it evidence on anything, on topaz with a plane or whatever? Is that a face I'm looking at, or is it a cleavage plane that I'm looking at? And because it continues to break in one direction, sometimes you'll see iridescence in cracks where it's starting to break, or you might see these little steps and stairs because it's showing you that it wants to keep breaking in that direction. So if you see steps and stairs or little iridescence, maybe you're looking at a cleavage plane and not a crystal face.
So if you're cutting a topaz, then where is ideally would you want that cleavage plane to be?
So there's our C-axis, there's our base. If I want the table, the flat top, the table, I will cut that 5 to 10 degrees off perpendicular to the C-axis. So it's just that little bit off.
Yeah, cool. Would it not split that? So if it doesn't have like a face that you need to polish, but like is it then more likely to just like snap in half if it was under pressure?
It could. See, I've seen some lovely imperial topaz cut like a kite shape, so it's really quite long, but only in a pendant, because if you had that on a ring, you could really end up cleaving it. So if it's a long thing with that's not so much support, but none of those facets have got to be in the direction of a cleavage plane. That applies to any gemstone with cleavage. You can't polish it.
And is that,
Don't press the enter key. Sorry?
I was going to say, is that why, like, if you have where you've got the facets that can have a likelihood of like chipping or cleaving at that, like
That's tenacity. So there's more than one thing about this durability
So I was going
thing.
to say, like, if you have a 5, like, obviously you've got that plane that you could cleave at, and then you're fastening at a 5-degree angle, but like right on that plane, like, would it be weaker?
That's to do with, see, we talk about hardness, which is about you're resistant to scratching, or we talk about being brittle, which means facet edges can break off. So you can have both. If you've got both, you're in trouble. So, you know, with a corundum, with a ruby, it's very hard. So unless it's had a life of 200 years and a tough life, it's not going to scratch. An emerald can be, an aquamarine, they've got 7.5 to 8 is a hardness. They're really hard, but they're brittle, so that the facet edges will break off because it's this different idea rather than scratching and hardness. They're all part of this durability bit. So different gemstones do different things with respect to those different things. So this is your lesson 3. So in your notes, it will show you differences. You need to know which directions something will cleave in, and examples of it. So cubic or octahedral, see fluorite, 4 directions, and so that's what you end up with. You don't, dodecahedral shape, none of the gemstones that you need to know about will have dodecahedral cleavage, because that's 12 directions of cleavage. Sorry, 6 on the 12 faces. Sphalerite you won't ever see. It's a sort of collector's gem, especially if it's faceted. But if you know some of these different cleavage, ways of cleaving, and an example of a gemstone to do that, that's what you need to know.
Jen, what's that thing there? What, the cool matchbox looking thing that to your left? Yeah,
This one?
What's that?
That is that'll be a monoclinic one.
Monoclinic?
Yeah, but you probably won't have to do that. See, any of those that one can be monoclinic. Depending on, it's showing you the directions it will cleave. Calcite is trigonal and it will cleave in those directions. So it's showing you what happens with the cleavage rather than what the original crystal would look like. But they're in your notes. Oh, okay. So this was an example that I was saying. This is parting. Now, parting means that if you've got twinning, that is a plane of weakness. It just so happens that in that plane where the parting happens. So if you've got lamellar or repeated twinning, at those particular angles, you could have a plane of weakness. So, but the white parting, for example, in ruby or sapphire, especially ruby, it is only at the twinning planes. So it's not cleavage where it's going to happen all the time in that direction. It is only where the twinning happens. So it happens in a particular direction, but only at particular spots, which is very different than cleavage, say with mica, where it's going to keep doing it all the time. This has only got that plane of weakness at the edges of twinning planes, and so they call that parting. And in this one, we've got sort of, I think you probably see that there's nearly 6 sides there for this crystal, and this parting they're showing you is at an angle, so it's not a basal parting, which you can also get with corundum. This is parallel to a rhombohedral face. So depends where your twinning is happening, where your weaknesses are.
Jen, how did you get 6 faces?
Well, I think if the C-axis is going down, I think you'd probably find that around there, if we looked hard, we would probably find 6 faces. It's not a good crystal. That's what I mean. Mother Nature doesn't always give us good crystals, but I'm expecting that because that's the direction of the rhombohedral plane, and that's definitely not a basal plane for a ruby crystal. So there would be, if we could look at it and look down on it properly, we could probably see evidence of about six sides. But you can also see with this lamellar twinning, you don't get V angles. It's only when there are something like geniculate twinning or Brazil law twinning or Japan law twinning. Geniculate twinning is in the tetragonal system. When I showed you rabbit's ears for a quartz, that's not geniculate twinning, okay? So that was called Japan law. So each of them have got their names. Fracture means if you hit something, it'll break. So everything will do that, and that happens in any direction other than a cleavage plane or a parting plane. So most gemstones, and when you do your hand lens, you might want to write down that what you see externally is a fracture. It's not going to help you be diagnostic in 99.99% of the time because, I don't know, 80 or 90% of gemstones can fracture in a particular way, but so can glass, so can paste. You see a thing that looks like a shell, that's a fracture, and that's called a conchoidal fracture, and it is the most common way a stone can break in a direction other than the cleaving and parting. So it's just got this fracture. So gemstones can do it, paste can do it. So paste is non-crystalline, so anything can have a fracture, and we can classify the fracture as of how clean is it? Is it conchoidal? If it's uneven. Splintery and hackly are 2 words that we usually keep for nephrite and jadeite because they are felted little baby. Remember, they were little crystals intergrown, so you get this felted appearance. So the way they fracture is very different because they're intertwined. That's just to show you later on. That's looking inside a gemstone, and it's a diamond inside a diamond. But there is a fracture because the lattice around that inclusion has upset the structure of the host diamond crystal, and so there is a fracture associated with that inclusion. So even though we're talking about fractures over an entire gemstone, you can see them inside stones with respect to a crystal inclusion sometimes. If you've got something inside it with uranium or thorium in it, because they're radioactive, you get breakdown around the crystal, the inclusion. So fractures can happen on the inside as well as the outside. That's just for interest. Oh, stop using the enter button. Sorry, guys. Now, tenacity is about toughness. Now, this is where our brittleness comes in. So this is about how easy something will absorb shocks. Again, know your definitions, but they're very simple. The ability to absorb shock without breaking. So as I said, a zircon is very brittle. if you when they travel around with zircons, they would not put zircons all in the same little brivka, in the same little paper together, because just the contact will mean that some of those zircons, even though they're really hard and they're bright, they are brittle, and so you'll get damage to the facet edges, just the same as you'll get damage to the facet edges of an emerald or an aquamarine, because their hardness is different than this property of toughness. Jade and nephrite, because they're all interlocking, they're quite tough, so they can carve them quite easily, whereas it'd be a lot harder to start carving something maybe with crisp edges in an emerald, because we've got a different amount of tenacity. They will ask you things like malleable. Malleable's easy. All the metals like silver, gold, copper, we use those in jewellery because they're malleable. We can bend and move them. So that's one way that they work. They can just move to absorb shock rather than be brittle and break off little bits. So, you know, brittle means you can get little bits of little grains breaking off. Malleable means that, you know, they don't do that. So you can know your definitions, and an example for each of those makes it easy to know. And again, they're only half or 1 mark questions, but if there's too many of the half 1 mark questions, you might be worried. So this is Laura from Melbourne. This was one of her stones that she took photos of, and you can see on the edges, see all those little edges, they're all quite abraded because that particular gemstone is showing signs of wear on the facet edges. It's a brittle stone. This one, now this one, when you're looking with your hand lens, did you get to look at a zircon?
Yeah.
Doubling, okay? That picture's just taken so you can see that it's still very brittle, because we're looking at everything doubled, but it's still all very brittle, and so we've got all of that damage to facet edges yet again.
Doubling's in the zircon and the peridot, right?
Doubling can happen in every gemstone but cubic system.
Oh, okay.
This is why you need to know, because next year when you're putting all your tests together, if you know which crystal system it is, so cubic system, there is no doubling.
Okay.
There's no.
Every other crystal system can produce doubling, but some of them, the doubling's easy to see, like peridot, zircon, tourmaline. Others, it's more gentler, so you need a microscope to maybe see it. Yep. I can show you a piece of calcite, and its doubling is way better than peridot and tourmaline, because you can see it when I put it down I do that on a weekend class. Put a bit of clear calcite down and you see 2 lines very easily sitting there, because the doubling in calcite is so big. Yep. So every crystal system but cubic. So one of the things, if we're looking for diamond or moissanite, which is one of the Johnny-come-latelys as a diamond imitation, moissanite's doubly refractive, and diamond comes from the cubic system, so is singly refractive. So that can be one of the clues between diamond and moissanite. Having said that, the way they cut the moissanite disguises that, but you've got to look for it. But
how do they disguise it?
The angle at which they cut.
Okay.
Sorry. So moissanite is in the hexagonal system from memory. So this is not it, but if we look down a C-axis with some of the crystal systems, when we look down that direction, it pretends to be singly refractive. If we look in other directions, we see the doubling. Mm-hmm. So sometimes there's a direction in a gemstone where it looks as if there's no doubling. Mm. So they cut the stone so that when you look down on the table, it looks singly refractive.
Okay.
So it looks like it's a diamond. You've got to turn it to see in a different direction to see the doubling. Optics coming up. Okay. So the hardness is the other one. Oh, my line's gone in the middle of that. I didn't mean to cross that out. Now that's just a mnemonic, because we know about Mohs scale of hardness going from 1 up to 10, with diamond being the toughest, the hardest. It's not a linear reaction by any chance, but most of it goes along like this, and then it goes right up really quickly to diamond, because it's so much harder than most things. moissanite's close, then we come down to things like corundum. So hardness, again, the definition, please, it's the resistance of a gemstone to abrasion. In other words, how easy is it to scratch? So when the fossicas go out, they have little things of known hardness. So if they want to, they can scratch something. So they'll have a steel drill, they'll have a penknife, they'll have, and then they can scratch to see which is harder and which is softer to give them a clue. Unfortunately, we can't do that on a gemstone because that's called a destructive test. But if you're out in the rough, that's what you use, this no scale of hardness, because anything's harder can cut. So a diamond can scratch anything below it because it's harder. And you do need to know the Mohs scale of hardness. And the girls can flirt, and other quaint things can do is the mnemonic. Just learn that and you know the Mohs scale of hardness. The girls can flirt and other quaint things can do. It's the first letter. There are others, but that's the one I learned. If you want to make your own mnemonic up,
Well, how do you do that?
the,
the bottom up.
the tau girls can
Oh my goodness.
TGC fluoro. The girls,
Make something up.
you make something up yourself if you don't like mine. I don't know.
Would you say that?
The geologists can fly and
Well, I had the giant cow flies aggressively over the Queen's tersely country diamonds. I only learned it on the weekend.
Yeah,
That's made it up.
so that's what I mean. You know, if you can find silly ways to remember things, it means you don't have to retain them. You can write that down in your, because one of the questions they'll often have is say, all right, put these stones in order of hardness from lowest to highest, or multiple choice. Which of these are correct? Have got which rows have got the?
I mean, these are just examples. So this is the examples that you'd like us to learn?
No, that's it, the scales.
That's
the
most
I know
scale
the
of
scale, but you're choosing only these
Oh, yeah, so
particular, and you know you want us to learn just these.
So they might have beryl, fluorite, apatite, and gypsum. And are they in the right order or the wrong order? From you know, that sort of thing. So if you know your gemstones and you know that, if it's multiple choice and says, all right, A, B, C, or D, which one has the gems in the right order? From lowest to highest hardness or whatever. If you know your mnemonic, you can do those easily.
Dan, can you go back to the 1 second? I just said last.
Yes. It's
Now remember, apart from your course notes, in Moodle, there are 2 glossaries. There's a simple one and there's a more complex one. Just start off with the simple one. All your definitions are in that as well as in being in your notes.
Jan, is this on Moodle? I can't find it.
Yeah.
It's an updated, it's in there, crystallography's there in the,
No, it's not. I just checked.
It's not. There's two of them. There's the older version.
Yeah, there are these ones. That's not in the.
Oh,
in the
that's
but,
oh, okay. I wonder why. Oh, this will go up tomorrow, I promise.
Thank you.
Okay, because 2023 was there. Oh, anyway, all right. Okay, going back to this one, I put an arrow there at 7. Now that's the magic number. Why?
Because that's what dust.
So all the grains of sand on a beach, what are they made out of?
Silica.
Sandstone, quartz, sand, quartz. And so they're tiny grains, tiny grains of quartz. Another understanding one. Okay, I've got a quartz crystal and I've got grains of sand. Have they got the same crystal structure?
Yes.
Yes, because they're both quartz, they're both crystalline, and so they've both got the same structure. Even though one's been broken down to little grains, they're the same thing. So all of the dust flying in the air is basically quartz. So if we want to wear something and have maximum use out of it every day and night, we need something with a hardness greater than 7. Anything that's got a hardness less than 7 needs more attention and care. Having said that, I know one lady who had this really expensive 5-stone white and pink diamond ring, and she went out in the backyard and built a rock wall, and then wondered why her ring was out of shape and she'd lost half the stone. So it's a matter of being sensible. Even if you've got diamonds, you don't go out to build that with pink diamonds and build a rock wall, and it cost an absolute fortune to make and then remake, because she never found those stones. Sorry?
They have insurance.
Well, it doesn't matter. It's still, I mean, it's just, to me, it's silly, you know. Like, that's all right, because I know some people have got to get buses. There's been a couple sneak out. Lesson 3 I left till the end. You can do it yourself, Nicole.
Thank you so much.
Yeah. Okay, now the hardness is important. There's always questions on hardness. Know about your hardness, your definition, and where your gemstones come. Anything that's organic is well and truly less than 7. That, if that helps at all, you do that later on in the end of the year. Thermal conductivity we used to mention more in the past, because once upon a time all shops had a thermal probe, and they'd have a clean diamond and they'd put it on the diamond and it would tell you if it was a diamond or not. And then along came moissanite, and moissanite reacts the same way with the thermal probe as a diamond. So there was a problem. So there are newer thermal probes now, which will separate them. But the idea of a thermal probe is some gemstones will move the heat through the gemstone and dissipate it really quickly. Some do it slowly. So the diamond will move the heat through quite well. A CZ doesn't. So we could always tell the difference between a diamond and a CZ. Now, from a gemology point of view, we never use that in the lab. We don't recommend it as a confirmation test. It is an indication perhaps. But if you're behind I put some other things in there, because if you're behind a shop front and some woman comes in and says, is this a blue aquamarine or is this a blue topaz? And they can look, the pale aqua and a pale blue topaz can look exactly the same. If you've got an old thermal probe, beryl does not move the needle at all, and topaz does, because their thermal conductivity can be quite different. So again, you're not confirming anything, but you could say to a customer, I would suggest without further investigation that what you may have there is a topaz. But so there are reasons why we care about what happens to heat passing through a gemstone, because the thermal probe is a little needle that you heat up, and then we see what happens to the heat when it touches the gemstone. So we used to teach more about that. Many years ago, there was a thermal probe in the lab that you could actually have a go with, but no more.
We've got lab diamonds as well now.
What will happen with those?
Exactly.
No, you tell me.
Oh, you're going to get a new machine to actually.
No. You tell me what's going to happen with a thermal conductivity probe.
It's going to be the same.
Yes.
Same as a diamond. Yeah.
Yes, because it's the same animal. Yes.
Yeah.
Cool. That's all I wanted to get to. So this again, this is not anything that you need to know, but if you're interested, some gemstones will give you magnetism. It all comes down, like colour and everything else, to electrons and poor lonely unpaired electrons that make all the difference with some of these things. So something like magnetite, which is part of the Sminel family, almandine garnet, if they've got a particular type of iron, not all irons, they can react to a magnet. Radioactivity, some stones have some radioactive stuff happening inside the gemstone. Green diamonds that are natural green diamonds, they've happened because radiation in the earth has made them green. We use radiation to change colour in gemstones if we want to, like blue topaz. So that's just for your interest about radioactivity and magnetism. And again, that's all I'm going to talk to you about, because that lesson 3, I haven't spent hours giving you definitions with tenacity or anything else, because it's all even, it's all straight. Simple, have something in your head for a definition of each of those, whether it's malleable and an example. Always have an example on hand because they'll often ask for an example to go with the definition. Questions? First in, best dressed. Whoever's got to drive the furthest, have another ready. I do not want to take them home.
I have another question.
Yes.
Thank you.
You're welcome. Hope to see you girls, boys.
I think I'm just gonna book the boy in.
Okay.
I think it might be, and after I knew it all.
Okay, good. Well, he can come back and tell her all about it, and then if she wants, she can do it the next time.
Yeah, exactly.
All right.
Okay.
Let Amy know
Because
first
to
thing in the
remember
morning.
the order of the
Okay.
Mohs scale. The graphite is first, then calcite, then
Gypsum.
gypsum.
Gypsum's
Right.
number one.
Oh,
No,
sorry.
it's like the lady with the pink
Oh,
diamond
sorry.
holding a.
Oh, sorry, I
I didn't
misunderstood.
understand that.
Oh, she went outside with her pink and white diamond ring on, and was actually physically building a rock
Building.
wall
I get that all
out the
the time.
back. The whole ring